Namaskar and a very good afternoon to all of you. Welcome to this colloquium. This is the first colloquium of this year. I would like to start by greeting all of you a very happy new year. Several of our colleagues have also joined through online in Mount Abu and Udaipur. I would also like to welcome them and greet them, and to all the people who will be watching this on YouTube as well. Today, we have a very distinguished speaker, Professor Marcus Bocher. He's a professor and a chair of astrophysics and space physics in Northwest University in South Africa. And it's my pleasure and honor to briefly introduce him to this audience. Professor Bocher obtained his PhD from the University of Bonn, Germany in 1997. And he has done his PhD at Max Planck Institute for Radio Astronomy in Bonn. And he was a postdoctoral fellow at the Rice University in Houston, Texas, from 97 to 2002, during which time he held NASA Chandra postdoctoral fellowship from 1999 to 2002. He became an assistant professor at Ohio University in Athens, Ohio in 2002, and an associate professor in 2007, and a full professor in 2012. Later on, he relocated to South Africa to assume the position of a charge chair of astrophysics and space physics at Northwest University in Potchefstroom. His area of expertise is in theoretical high-energy astrophysics, with a special emphasis on extragalactic sources, including active galactic nuclei and gamma-ray bursts. He is the chair of the South African Gamma-ray Astronomy Program, coordinating the high-energy astrophysics research activities and founding needs of approximately 100 members across 6 institutions in South Africa and Namibia. Today, he's here. He had a very good, visit to our observatory in Mount Abu. Today, he had some lab visits, a few labs in PRL, and we look forward to his lecture, this colloquium, in a very interdisciplinary and very exciting topic of multi-wavelength polarization as a probe of astrophysical relativistic jets. So with this brief introduction, I'll request Professor Marcus Bocher to please come on the dais. Please give a big hand to him. That's no problem. So then, okay. Thank you very much for the introduction. And in particular, thanks very much to everybody who gave me this great tour of all the labs here. It was really, really amazing, fascinating to see what great work is being done here and what great facilities are here. Kind of makes me jealous as a pure theorist to see all those nice labs, because ultimately the only lab I ever had was this one. And
even that was a mix of Labrador and Golden Retriever, and she died a couple of years ago. So that's all the lab I ever had. So really jealous about that. And before I really dig into the topic of my talk, maybe most of you probably know where Potchefstroom is, but just in case somebody doesn't. So where I'm based right now is in South Africa, north central South Africa, about 120 kilometers west of Johannesburg. So this is the small town of Potchefstroom. What many of you may know about South Africa is that there's the Kruger National Park that's world renowned for its wildlife. It's the northeast part of the country of South Africa. Maybe a bit of a critical issue here is that I think that some of the best wine in the world is made in South Africa and the Cape region. So if ever you get out of Gujarat, please try some. So where we are is actually quite close to the Kalahari Desert. It's kind of semi-desert. We're in the outskirts there. So this is kind of the natural landscape of where I am. It's not savannah. This is a nearby national park where we have all the big five there. This is some of the pictures I took in that national park, pretty close to where I live. So reason to come to South Africa. First reason, of course, being the wine, but more professional reasons is the astronomy developments that are going on in South Africa. In particular, first and foremost, what's really driving a lot of investment in astronomy in South Africa is the square kilometer array that started with the Meerkat radio telescope array, an array of 64 16-meter dishes in the Karoo area of South Africa that will eventually grow into the SKA, the square kilometer array all over Southern Africa. In addition, most relevant for myself is actually that we're very heavily involved in HESS, the High Energy Stereoscopic System, the world's largest currently operating ground-based gamma ray observatory near Windhoek in Namibia. And there's the largest single optical telescope in the Southern Hemisphere, the Southern African Large Telescope near Sutherland, also in South Africa. And as has already been said, we are organized in the South African Gamma Ray Astronomy Program that I am chairing with about 100 members at 6 institutions in Potchefstroom, 2 universities in Johannesburg and Bloemfontein, the South African Astronomical Observatory in Cape Town, and the University of Namibia. We're all coordinated in this Gamma Ray Astronomy Program. So the main reason of these activities that actually brought me to South Africa from the US. Coming to the actual topic of my talk. Galaxies. It'll be about active galaxies, a very special class of active galaxies. Galaxies, as you know, host essentially all stars and planets in the universe, come in all different kinds of shapes and sizes. Our own Milky Way could travel a couple 100,000 light years out of the galaxy, would look pretty much like that, and our sun would be somewhere like 25,000 light years away from the center of this galaxy. We know that pretty much all these galaxies that we see throughout the universe have a central supermassive black hole in their center. So this is actually the first light Meerkat image of the central region of our Milky Way. And you see the region of this central supermassive black hole. While it's shining, there is something going on, but nothing really spectacular there. In fact, the way that we know that there actually is a black hole, this discovery was in fact the subject of the Physics Nobel Prize in 2020 through Reinhard Genzel and Roger Penrose for the theoretical underpinning, was through observations in the infrared of stars near the central region of our Milky Way. So this is really the gravitational center of this cluster of stars. And the way they are moving clearly indicated that there's a very large mass of about 4 million solar masses that cannot be anything else than a black hole. So from that almost direct evidence, we know that there is a black hole of 4 million solar masses in our own Milky Way. And we have similar evidence from this detailed kind of observations, but we know pretty much for sure that every other galaxy in the universe has a supermassive black hole of millions and even billions of times the mass of our sun. In the case of our sun, this black hole is actually remarkably boring in the sense that it doesn't have a lot of gas to accrete around it. It's very quiet. There are much smaller solar mass black holes. They're way brighter in its rays than this supermassive black hole of 4 million solar masses. So this is quite different in galaxies that we call active galaxies, where this black hole actually has a lot of gas and dust to accrete on it. So there are active galaxies that have these extreme properties where this central region of this active galaxy actually outshines all hundreds of billions of stars in this galaxy from a region that we know is only as tiny as about the size of our solar system. Solar system, those of you who are not astronomers, may seem large to you, but compared to the size of the galaxy is really just a tiny little dot. And that outshines the entire galaxy by hundreds, thousands, or even many thousands of times. We know that they're so small because they're very rapidly variable. I'll say more about that in a bit. They are the most numerous sources of high energy X-ray and gamma ray emission outside of our own Milky Way. Their optical spectra show evidence that there's energetic radiation ionizing gas in the central region. My talk will be all about polarization later on. So they show high polarization in radio, optical, some in X-rays. And in particular for these blazars that I'll talk about is these jets. Some of these show highly relativistic collimated outflows called jets. And we know for sure by now that these are powered by accretion of mass of gas onto that central supermassive black hole. Interesting thing here is that, so we have a supermassive black hole here, there's gas that feeds that accretion flow into an accretion disk that flattens off and heats up to millions of degrees. We have gas clouds here that are ionized by this hot accretion flow that gives us these emission lines. And along with that accretion of mass onto the black hole, not everything is lost. There's actually these relativistic streams of gas moving with almost the speed of light perpendicular to this accretion flow. In the innermost region, somehow this accretion flow and the black hole manage to shoot out these jets with essentially the speed of light. Now, these jets do something further out on many, much larger scales than the actual accretion flow, actually larger scales than the entire galaxy that this black hole is located in. Depending on how this is oriented with respect to us, if we happen to see this thing kind of from the side, and we don't actually see much of the jet right in the inner part, we only see on much larger scales. The scales here are much larger than the actual galaxy, which is really just about the size of this little point here, where these jets ultimately dissipate. They produce shocks that accelerate particles. They produce radio emission, and we see these as bright radio sources. What you see here is a real image in radio waves of one of these radio galaxies, one of these radio loud active galaxies. Now, there are occasional cases where we actually happen to see these jets almost right down the barrel, so almost right down the jet. And in that case, we have special relativity effects that very strongly amplify the radiation that goes in the forward direction, in the direction of the jets that we're looking right into. So in that case, we see images like this, where it kind of looks like there's only one jet here. Of course, that's not true. It happens same on both sides. But the emission from the jet coming towards us is so much enhanced by relativity effects that we see that so much brighter than the other jet going in the other direction. The same jet is going away from us, but that's boosted away from us, so we don't actually see it. And this is the kind of sources that we call lasers. So these are the special class of radio loud beamed AGN, active galactic nuclei, that consist of like objects and quasars. These are the ones that show very rapid variability. Often this region, again, remember that outshine hundreds of billions of stars from this small region, and they can be varying in scales of just hours, or even less than hours. There's bright gamma ray sources, and I'll say a bit about this superluminal motion. Sounds like science fiction, but it really isn't. And they have the polarization that I will talk much more about in a bit. So this illustrates some of the polarizations. All of this is light curves. So there's time on the x-axis and various fluxes on the y-axis. This is high energy gamma rays by the Fermi Gamma Ray Space Telescope. Here we have X-rays, we have optical. We also have polarization in the optical, the degree of polarization means the amount by which the light is polarized, polarization angle. And you see all of this is varying on a huge variety of time scales. So this whole range here is something of the order of 4 months or so. You see everything is going up and down in kind of random fashions. And most confusingly, it's not all going up and down in the same way. So sometimes one band goes up, the other one stays where it is, and the other way around. So it's very chaotic, unpredictable variability we see here, not only in flux, but also the polarization signatures that I will focus on in the rest of my talk. So if we plot their spectra, their broadband spectra across the entire electromagnetic spectrum, so we have here in frequencies, we start from radio, there's infrared, here optical, X-rays, and there's gamma rays here. We see that they are emitting, they can be detected across the entire electromagnetic spectrum, from radio waves all the way to the highest energy gamma rays. We see that the broadness of the spectrum is much more than what you expect from something like stars or so, that emit essentially only in maybe infrared, optical, ultraviolet. There's nothing on broader range. This clearly shows us that it's not something that is just hot gas or something. It's processes we call non-thermal, so relativistic electrons in a broad distribution of energies, way beyond anything that you can describe with a temperature. So there's a low energy component of this spectral energy distribution that we pretty well understand to be synchrotron radiation. I'll introduce that in a minute. And there's a high energy component that goes from X-rays to gamma rays. That is not quite clear what actually produces that. I will discuss the possibilities in a second. So we classify those, just a brief introduction, by where this low energy component, the synchrotron component, peaks. This can be at low frequencies. This is below the optical. We have the optical infrared range here. So in this class of low synchrotron peak lasers, we have that synchrotron peak kind of below the optical at lower frequencies than optical. And here quite often, actually, the gamma ray output dominates the entire electromagnetic output. So even if they may look bright in the visible light that we see, there's actually much more energy coming out, even at the highest energies at gamma rays. And then we have the other extreme where the synchrotron dominates, but it peaks. Here we're talking about X-rays. This is hard X-rays. So we have some of these blazars where the synchrotron spectrum actually peaks way in the X-rays, way higher than at the low synchrotron peak sources. Here we talk about high synchrotron peak blazars. Almost all of these are, or all known of these are BL-Luck objects, and quite often the synchrotron output actually dominates over the high energy output. So in this case, the X-rays dominates the total output in radiation. And then there's sources in between where the synchrotron somewhere peaks in the optical. So these are intermediate synchrotron peaked lasers. So now I talked about this superluminal motion. What is that? This is an actual sequence of real observational data, very high resolution radio observations, where you see the core of this active galaxy sitting here. So the supermassive black hole that powers this AGN is sitting somewhere here. And we see components of this jet moving out over time. You see time ticking away here, year after year. So the whole sequence, I think, is something about 10 years or so. So that appears kind of slow, but we know that this thing is like a third of the way across the universe from us, across the visible universe. So it's very far away. Even though this looks slow, we can convert this into a linear velocity. And if we do that for many of these sources, we find that that is something like 10, 20, 30 times the speed of light. Again, that kind of sounds like science fiction, but luckily it's not. It is true. We see this, and this is just an effect of light having a finite travel time and of this stuff here moving out with almost the speed of light. So what's happening is this. We see our emission region moving across the jet here. It's emitting radio waves or light that travels towards us. In this case, we are sitting out here somewhere to the right. And as this is moving with almost the speed of light, it's almost catching up with the light that it's just emitted. So there's quite a long time elapsed from the region being here to being here. But the time that we actually see is much, much shorter than that, because all the light information is bunched up in a very short succession. So that gives us the impression that this happens on a much shorter time than it actually does. And well, speed is distance over time. If we compress the time, then it makes us believe that the speed is so much higher. That actually tricks us into believing that this is moving faster than the speed of light, which it really isn't. But it gives us a lower limit to the relativistic Doppler factor here and the Lorentz factor. Namely, if we see this moving at 10, 20, 30, 40 times the speed of light, that gives us a lower limit to the speed, to the Lorentz factor with which stuff needs to be moving. What does that do to the observed radiation? So let's assume our red blob there, if we move along with it, is radiating the same way in all directions. Then what that does is it boosts the fluxes, the intensities, by 3 factors of this Doppler factor. So if the Doppler factor is, say, 10, then the intensity suddenly is enhanced by a factor 1,000. The frequencies are shifted, blue shifted to higher frequencies. So what might come out in hard X-rays, actually we see in soft gamma rays. And also the variability is shortened, just a similar effect to this light travel time effect that we see. So if this moves with a Lorentz factor of 20 or so, we see the variability actually 20 times faster than it actually is in the source. So the sources are not that extreme. It's only these relativity effects that trick us into believing that they are so extremely bright and so extremely rapidly variable. In particular, if we now have a spectrum that we put in nu f nu, so it's frequency times spectral flux, we have a component like this, the synchrotron component. It's boosted up by 1 Doppler factor. And in this representation, it's boosted up in flux by 4 factors of the Doppler factor. So if we use that flux to infer just if we are tricked into believing that it's radiating in all directions, we just take 4 pi times distance squared times that flux to give us a luminosity. But that gives us an estimate that is 4 factors of a Doppler factor too large. So for a Doppler factor of 10, we would overestimate the luminosity by a factor of 10,000. But this is the reason why we see these sources, so many of them, and why they are so bright in gamma rays, why they are the most numerous gamma ray sources, because there are these weird special relativity effects that shifts everything to higher energies and makes them so much brighter. That's why we see them so well, and that's why we can study them so well. So now, as physicists, we're primarily interested in what makes the radiation. If we see radiation, especially going all the way into the gamma rays, somehow we need to understand what radiates and how. So the way, well, the non-astrophysicists, the way that we produce radiation, that astrophysical sources produce radiation, the main mechanisms are these. Synchrotron radiation, that means we have a relativistic electron or proton that spirals in a magnetic field. And from electrodynamics, one of the most important results is that an accelerated motion, spiraling, is an accelerated motion, an accelerated charge radiates. The radiation we see when that happens in a magnetic field, we call synchrotron radiation. That's what makes up almost certainly the radio all the way to optical ultraviolet or even X-rays in our blazars. Relativistic electrons can also scatter low energy photons. If an electron is very highly relativistic, meaning moving with almost the speed of light, it can interact with a low energy like optical or infrared photon and scatter that up to higher energies. That can make X-rays to gamma rays. That's a way to produce the high energy radiation. But we can also have very high energy protons. So if we have protons that interact with low energy photons, they can go through a nuclear resonance to produce either neutral or charged pion. And then, well, pions are unstable particles. They either decay into two gamma rays as their neutral pions or charged pions, decaying into muons that further decay into positrons then. And that way we can also get neutrinos. So that gives the fundamental radiation mechanisms that we're dealing with for these blazars. So the basic classes of models that we apply to produce the broadband radiation from blazars are either leptonic or hadronic models. Obviously, we know that this is kind of a complicated system. The jets are probably not perfectly straight. There's extended sources. But for the simplest consideration of just the radiation physics that's happening there, the particle acceleration, typically when the physicists among you know the typical spherical cow assumption. So whenever we have some kind of physical system, we assume it's spherical. We don't assume it's in thermodynamic equilibrium, but at least it's spherical. So by now for cows, obviously, we know that's a good approximation. So they are spherical. But for blazar jets, that may not hold. But for just the basic picture, a holistic view, so to say, we can just assume that they're spherical for first approximation. So let's assume we have our cow-shaped emission region there, where we accelerate electrons to relativistic energies. Then, well, that will be, we don't need to talk about the details here. We'll get some kind of relativistic electron distribution that in leptonic models that makes up the synchrotron emission, the low energy component of the spectral energy distribution. And then the high energy radiation is produced by the Compton scattering, by Compton upscattering of either the synchrotron photons themselves, or there's the accretion disk radiates, that radiation can be upscattered, or the dusty torus or these line emission regions. There's plenty of sources of photons that can be upscattered to make the gamma rays in these models. Alternatively, we can have models where also the protons get accelerated to extremely high energies. Then we still make the low energy radiation by electron synchrotron. But then we have the high energy protons that could potentially dominate the high energy output. Protons are charged particles that can also radiate synchrotron, or we can have these pion production processes that we just mentioned. So neutral pions decaying into two high energy gamma rays, charged pions decaying into muons and onto electrons, positrons. Most importantly with that produces 3 neutrinos for every interaction that happens. And there's a recent development that we know that probably at least some of the neutrinos that have been seen from astrophysical sources by instruments like IceCube on the South Pole are probably actually made in the jets of these blazars. What complicates the matter here is that the radiation from these processes comes out at extremely high energies where the gamma rays can't actually get out. They get absorbed, like electron-positron pairs that radiate more high energy radiation that still can't out, get absorbed again, make more pairs. We produce a whole cascade of electrons, positrons that ultimately radiate at energies where the radiation can get out. So that complicates the calculation of these models. So now we use and study these models and many other things we do to figure out many of the open questions. There's a lot that we still don't understand about these blazars and active galactic nuclei in general. In particular, what makes these jets? Well, how do these jets get their energy? It can be either from the magnetic field of the black hole, or it can be from the accretion disk. So what launches them? Why do they stay collimated? We see these things ejected from a tiny little region in the center of that galaxy, and then they stay straight without being dissipated for thousands, tens of thousands of light years. How do they do that? It's really not clear at this point. What do the magnetic fields do to that? What are the jets made of? We don't even know that, if they're electron-positron pair jets or normal electron-proton plasma. What accelerates the particles to be energies that can actually make the high energy gamma rays that we see, and where all that happens, even that we don't know. So you can say Why don't we just apply these models and see if leptonic or hadronic models are favored to make the broad band spectral energy distribution? Upshot of that is that doesn't really tell you much. You see here in red a leptonic model, in green a hadronic model, and typically both models can give you an equally good answer. So upshot is just looking at spectral energy distributions doesn't really help you answer any of these questions, really. It just gives you some parameters of different models, but that doesn't answer the question. So we need more to distinguish what makes these high energy emissions. Neutrinos, of course, would be a telltale signature of protons being accelerated. Variability patterns actually can be different between the different models. But what I'll focus on now is polarization can actually give you very important diagnostics on the physics of laser emission. So what is polarization? As you know, light, like any other electromagnetic radiation, is oscillations of electric and magnetic fields that just propagate along from the source to us, with electric and magnetic fields oscillating perpendicular to each other. Now, typically, for most sources, like light bulbs here, these fields are oscillating kind of in random directions, have to be perpendicular to the direction of propagation, but otherwise they're pretty much random. If light is polarized, the electron oscillation direction has a preferred direction. So if, say, the electrons are preferentially, the electric fields are preferentially oscillating here in the vertical direction, then we say the light is polarized. So from synchrotron theory, we know that actually a non-thermal relativistic electron distribution gives you a very characteristic degree of polarization that is related to the spectral index of that electron distribution, or the radiation spectrum index here. That means if we had a perfectly ordered magnetic field, we would see polarization in the synchrotron of up to about 70 or more %, which clearly we don't. And realistically, I mean, in a complicated system like this, you don't expect a nicely, perfectly ordered magnetic field there. So clearly, there's something more chaotic, something more turbulent there. And the lower degree of polarization tells you that that's the case. But also, this Compton scattering process can be polarized. I promise that's the only somewhat more involved equation I have in this talk, but just to illustrate how the scattering of a photon by an electron can induce polarization. So here we have epsilon as the normalized to the electron rest mass energy, the energy of the photon before and after scattering, epsilon and epsilon prime. And we have E and E prime, the directions of the electric field vector of the polarized X-ray or whatever comes in before and after scattering. Now, in a regime that we call Thomson regime, that's the relatively low energy regime, where the photon essentially bounces off with the same energy with which it comes in. So it's elastic scattering. So in that case, in the electron frame, we have the same energy before and after scattering. Epsilon is epsilon prime. And we are 1 + 1 - 2. This all cancels out. We're only left with this dot product here. And now assume that an X-ray comes in with a polarization vertical, and you try to scatter it up in the vertical direction, then, well, the new polarization direction would have to be perpendicular to that, right? It has to be perpendicular to the propagation direction. But then the new polarization direction is perpendicular to the old one. So E and E prime are perpendicular to each other. Then that dot product vanishes, and this doesn't happen. So that means this tells you that you're preferentially scattering in the direction, in the plane of the perpendicular to the polarization, and you tend to preserve the polarization. But if you scatter off to the side, you will preferentially preserve that polarization direction. That way you induce polarization. So if you had a situation where radiation comes in here from the top, You scatter off, you watch this scattering from the side. You filter out the polarization that's in the plane perpendicular to the screen. Because light that's polarized this way would have to be scattered in the direction of its polarization. That doesn't happen. So you filter out this polarization direction, you see the scattered light polarized in the plane here perpendicular to the screen. So that way polarization can be induced just by Compton scattering. Maybe quickly, if the target photons are not polarized, but the electrons are relativistic, then all these anisotropy effects will be smeared out by special relativity effects. You don't see any polarization. If the target photons are polarized, like on synchrotron, self-Compton scattering, if synchrotron scattering off, if the Compton scattering of the synchrotron radiation makes the high energy radiation, then you'd expect a somewhat lower polarization than synchrotron, about half of it. And that gets more reduced if this region is not perfectly ordered. So now, why is all this relevant? If you make predictions for polarization, obviously you want to try to measure that and try to test them. How can one measure X-ray polarization? One way is to exploit exactly this polarization dependence of the Compton scattering. So if an X-ray photon comes in, it's polarized. You can build a detector like it's realized in this CZT detector on the Indian Astrosat satellite, that you have one Compton scattering, and then you try to detect the photon after scattering. Then let's assume you have synchrotron radiation coming in on a magnetic field, projected onto the plane of the sky. Polarization direction is perpendicular to that. Then the scattering here will happen in the plane perpendicular to the polarization direction. So you'd expect to detect your photons in this ring around the scattering with an azimuthal asymmetry. You expect preferentially to see the photons perpendicular to that polarization direction. So this angular modulation of the X-rays that you detect actually in your detector will give you a measure of the polarization of the X-rays. This has been realized indeed in the Astrosat satellite. Alternatively, one can exploit the photoelectric effect. That's an effect where X-rays are coming in, hitting an atomic material, so atomic nuclei, electrons around it. X-rays kick out some of these electrons, ionize the atoms, and the electrons kicked out are being ejected primarily in the plane of the polarization. So in this case, in the plane of the screen. So that way, we get actually the opposite effect. We get the electrons being kicked out in the direction of the polarization, but the method is the same. You look for an angular asymmetry of the ejected electrons, and that gives you a measure of the polarization. So this has been realized in the first dedicated X-ray polarimetry satellite called IXPE, the Imaging X-ray Polarimetry Explorer, that was launched in 2021. Exploits this polarization dependence of the photoelectric effect, measures X-rays in the 2 to 8 kilo-electron volt energy range. So a quick run through what one expects to see now if we measure polarization, say not only in X-rays, but across the electromagnetic spectrum. So we look here at the spectrum from, again, radio waves through infrared, optical, here's X-rays, and gamma rays. Then first, well, we expect to see some signatures of the accretion disk that's typically emitting in the optical to ultraviolet. There's this dusty torus that actually feeds the accretion disk eventually, that feeds at infrared energies. This is our thermal radiation that we don't expect to be polarized. So that contributes some unpolarized radiation here. Then if it's a leptonic emission scenario, the electrons make all the radiating in our blazar jet. Then we have synchrotron radiation here. That can be highly polarized, but where there's a significant contribution from the dust torus or the accretion disk, that dilutes the polarization. So we see only the polarization of the total emission, the sum of all of this. If that's dominated, say, by the accretion disk, then it's almost unpolarized, even though the synchrotron component is polarized. So we see some maybe complicated frequency dependence of the polarization. At higher energies, if we have synchrotron self-Compton, that can have some degree of polarization lower than synchrotron. And then there's external Compton that will be unpolarized. If the high energy emission is made by hadrons, then essentially everything that comes out there is either proton synchrotron or it's synchrotron radiation from these cascades. That's all highly polarized, so you expect much higher degree of polarization here in the X-rays and potentially gamma rays. So that would be a way to distinguish actually what makes the high energy emission. If you see this high energy emission polarized, you have a pretty good indication that there's actually protons making the radiation. If it's electrons, you would expect very low polarization. This is some specific model prediction made by a former PhD student of mine long before X-ray and gamma ray polarization was actually realized. In intermediate synchrotron peak blazar, so this is specifically for a blazar. Here's the SED from ultraviolet all the way to gamma rays, from blazar where the synchrotron really peaks at low frequencies, and you see only the high energy component here in X-rays. There you expect low degree of polarization for electronic, high degree for hadronic emission. In intermediate peak sources, you can have some kind of contribution from the synchrotron. You could actually get higher X-ray polarization. Now, actual observations. Of course, IXPE has been operating since 2021, or really since 2022. So there have been many observations of blazars by IXPE. This is one example of a typical low-frequency peaked BL-LUC objects, actually the one that gave the name to the class of BL-LUC objects, has been observed multiple times by now. In each case, we don't measure any X-ray polarization. Most importantly, we measure the X-ray polarization much lower than the optical polarization. That actually gives a pretty strong indication that it's not hadronic emission that makes the high energy radiation. So most likely it's synchrotron self-Compton that dominates the high energy emission. That's been done for a few other low synchrotron peak blazars as well, and all systematically. You see here, we haven't introduced Stokes parameters, but this distance of this central point from 0 here gives you a measure of the degree of polarization. In each case, it's perfectly consistent with 0. So for all of these blazars where the synchrotron peaks at low frequencies, we systematically see no high energy polarization. That's a very strong indication that the high energy emission here is really made by electrons and not by protons. There's one other application of polarization that I've already alluded to. So if we have a spectral energy distribution here from, again, this is the optical range, where, say, we have the optical emission dominated by synchrotron radiation, but there's some contribution from the accretion disk coming in. You would expect the degree of polarization to actually decrease where the accretion disk makes a substantial contribution. This can in fact be measured by a method called spectropolarimetry. If you can split up the measurement of polarization in the optical as a function of frequency or wavelength, you can measure this. You can see if it's consistent with just being synchrotron with a constant polarization degree or whether it declines. And one of my former PhD students has developed a code to model this spectropolarimetry together with spectral energy distribution data, and has really been able to pinpoint the contribution that the accretion disk makes to the total emission here, which could otherwise not be distinguished. It's only this polarimetry information that tells you that we can say there is a substantial contribution from accretion disk coming in. You see here as a function of frequency, the degree of polarization, as it systematically decreases towards higher frequencies. There's emission lines that are unpolarized, that again decrease the total polarization. So we could come up with this fit that really pinpoints the contribution of the accretion disk there and effectively measure what the mass of the black hole is. By measuring the spectrum of the accretion disk, you can in fact pinpoint the mass of the black hole that drives the system. Okay, back to IXPE results. We now look at these blazars where the synchrotron beats at high frequencies. There, the X-rays are actually dominated by synchrotron radiation. And here, an interesting result came up. This was predicted already long before IXPE launch, that if you have something like a shock going through your jet that accelerates particles at the same time, compresses the magnetic field, makes it well ordered, you have the highest energy particles that are just accelerated at the shock, seeing a very nicely ordered magnetic field, whereas the particles then diffuse away behind the shock and cool to lower energies. They radiate at lower frequencies. But on the larger scales, the magnetic field becomes more disordered again. They see a less ordered magnetic field. The lower energy radiation should be less polarized then. So there's some model predictions that were made long before IXPE observations. And an interesting, one of the maybe most important results from IXPE on blazars is that that has been confirmed. So here's one of the prototypical high energy peaked BL-Luck objects, Macquarian 541, where IXPE has seen in many observations so far that there's a significant degree of polarization. And in particular, the polarization is much higher in X-rays than in optical. So here's as a function of frequencies. We have radio here, infrared is somewhere in between. Here's optical and X-rays. The degree of polarization systematically is much higher in X-rays than in optical and lower frequencies. We see exactly what was predicted there. That's the highest energy radiation in synchrotron. It's more highly polarized than lower frequencies. You have the stratification, highest energies, highest degree of polarization. The lower you go, the lower the degree of polarization. This also as a function of time. The trend holds essentially for all times. So yeah, nice, really confirmation of a theoretical prediction, theoretical picture. All good now, but actually not that simple. Of course, blazars always surprise us with new things that we don't expect. And that was seen in this, the other prototypical gamma ray, very high energy gamma ray blazar, Macquarian 421. But we do see the same thing, that the X-ray polarization is significantly higher than the optical. We see the degree of polarization here for X-rays with the red and blue points as a function of time here. And the green crosses are the optical, that's significantly lower than the X-rays. But here we have the polarization angle. So the orientation of the polarization direction, where you see the blue and the red points here, showing that that actually rotates around by more than a full rotation. So during this observation of about 2 weeks or so, the X-ray polarization angle rotates around by more than one full rotation. Whereas in the optical and other bands, the polarization angle stays still. Now that's totally not what you expect from a scenario where you have just one jet, one coherent magnetic field structure. Yet you see synchrotron radiation from all particles, but the lower energy particles see a magnetic field with one orientation that stays where it is, whereas the X-rays rotate around. So this, to my knowledge, has not been explained by anybody yet. It was completely unexpected. And there's a weird opposite case, in fact, by another high synchrotron beat blazar, where again we see X-ray higher than optical polarization, that we see in all of them. But here, well, there's the degree, the angle of polarization at the black points is X-rays. Over time here, that's the IXP observations were no significant change for the X-rays, but the optical was something weird. So here we have the X-ray polarization staying where it is, and the optical kind of rotating one way, then going back. And well, we think this is the same emission geometry, but it can't really be. So again, no clue what actually does that. So this is clearly a mystery that one needs to look at with theoretical models. To my knowledge, none have been able to explain that. So this is kind of a summary of the high synchrotron peak BLAC objects. We see systematically for the different high synchrotron peak BLAC objects, the X-ray polarization in black is higher than the optical polarization in blue, and the infrared in red, and radio in green. And the same even, so the ratio of X-ray to optical polarization as a function of X-ray polarization. Also, that increases the higher the polarization in X-rays, the more extreme that difference between X-ray and optical polarization becomes. So it's a very nice, consistent picture in this sense that we have this clear evidence for energy stratification. Highest energy electrons see the most ordered magnetic fields. The lower the energy is, the more extended the emission region, the more disordered the magnetic fields. And that brings me to my summary. I've shown about hadronic particle emission that could be diagnosed by measurable X-ray polarization, which is not seen. So there seems to be very strong evidence that in the low synchrotron peak blazars, where the X-rays are the high energy emission, it's most likely leptonic emission, so electrons making synchrotron self-Compton to produce the X-rays. Talked a bit about this optical spectropolarimetry. So one can use spectrally resolved polarimetry to distinguish thermal and non-thermal radiation components. And in that one case is effectively measure the mass of a black hole that produced the accretion disk spectrum. And for these high synchrotron peaked lasers where the X-rays are made by synchrotron radiation, we see clear evidence for synchrotron always being, the X-rays always being the highest polarized over optical, infrared, and radio. So evidence for this energy stratification that the highest energy electrons see the most highly ordered magnetic fields, and they get less and less ordered the lower the energy is. Thank you.
So thank you very much, Professor Boucher, for extremely lucid and nicely explaining talk, very complex concepts like your polarization, origin and detection of polarization, particularly superluminal motion. So it was very nice. And I would also like to mention that X-ray polarization measurements are an important part which we are looking forward for Indian X-ray astronomy community, which we are looking particularly in terms of observational new programs post AstroSat. So, and Blazar forms a very important science subject for it, and you have established the importance of it very well. So it was very helpful. Thank you very much. So the talk is now open for questions. Yeah, Viresh.
Yeah, thank you, Marcus, for a great talk. You saw that in one of the source, X-ray polarization angle is rotating.
Hmm.
So, what could be the reason for that? Is it like magnetic field which is twisting around and that is causing the rotational polarization angle?
As I said, I have not come across a really coherent explanation for that, because it's
Okay.
really not what you expect in this scenario of stratification, where you have one coherent magnetic field structure and you have just particles moving through. It's honest answer, I don't know, and I don't think anybody knows.
Thank you.
Yeah, Namit.
Thank you, Marcus, for an interesting talk. I have two questions. First is regarding the length scale over which you would like the magnetic field to be ordered. How is there a way to estimate that, or to expect what length scales the magnetic field should be ordered? The second one is related to neutrinos. If you do see neutrinos, but the polarization data does not seem to prefer the hadronic model, what could be the source of neutrinos in that case?
Okay, the length scale is something of the order of the propagation of the material post-shock away from the shock, which is probably close to at least, I mean, this is probably of the order of the speed of light. All the motions are relativistic. So from the time that we see things varying, it's probably of order of days or so typically. So that means we're dealing with probably scales of some of the order of, with Lorentz contraction of the time, some 10 to 15, 10 to 16 centimeters or so. It's probably a typical length on which these things evolve. Within neutrinos, in fact, that would be a whole different talk. But the upshot there is that there have been quite a number of potential coincidences between neutrino events and gamma ray flaring blazars. In almost all modeling attempts, it turns out that it's very strongly preferred that the hadronic component to the SED is actually subdominant. So even if neutrinos are produced by relativistic protons that are there, they are unlikely to make a substantial contribution to the spectral energy distribution. So otherwise, there's very strict constraints from the X-ray flux, actually. If there's photopion productions making a strong contribution, then we have these electromagnetic cascades induced that have a very flat spectrum towards lower frequencies to X-rays. So if that makes a very bright gamma ray emission, the predicted X-ray flux is typically too high compared to what's measured. So that puts a very stringent constraint on the contribution of protons to the SED. So most likely that is subdominant. So it's still consistent with, say, low synchrotron peak blazar making the neutrinos, but at the same time, the X-rays actually being synchrotron self-Compton dominated, so electronically dominated.
But is there a possibility of a completely leptonic scenario, but still producing neutrinos via some complicated mechanism?
I mean, you need protons to make neutrinos. You don't get neutrinos out of a purely leptonic scenario, not in any plausible way.
E gamma to E nu nu bar, the reverse of E plus E minus to nu nu bar gamma, which is used to measure the neutrino count at LEP. But the cross section is going to be small.
Yeah,
it's
theoretically possible, but this is very, very inefficient. So I think it's very unlikely.
Thanks. Any, yeah. So,
Marcus, you mentioned about the issue of understanding the collimation, because it goes to several light years, it still remains confined. So where does our understanding stands there on this aspect? And what do we know which could be contributing to that? We know that ambient media is very thin. So whether it gets pressed and then yes, there's a background or what?
I mean, there's some understanding now that yes, ambient medium can play a role, but also limited because you produce strong shear layers if that makes too strong an impression. But also just magnetic field structure can actually help. But if you have helical or toroidal magnetic field structures, they can actually help with hoop stresses to collimate a flow that is going along the colloidal direction. So there are plasma physics models that can support that. But still, it's a very tricky business to really suppress plasma instabilities that you might expect. But somehow these jets manage to do it. And most likely it's the colloidal magnetic field structure that really helps to collimate, so keep the jets collimated.
yeah.
Yeah, thank you very much for a very nice talk. So my question is, this synchrotron photons are primarily the seed photons for the high energy photons.
Sorry?
Synchrotron photons are primarily the seed photons for non-thermal component of emission, right?
Not necessarily. Most likely for the X-rays, at least in these low synchrotron peak blazars. In these blazars, the higher energy emission is most likely actually external Compton scattering. So if we look at a source like this, for example, we have synchrotron self-Compton, but there's most likely very significant contribution from external Compton scattering. If we have these SEDs that are very strongly Compton dominated, that's very difficult to do with synchrotron self-Compton only. So most likely it's indeed external Compton scattering that makes the dominant contribution in the gamma ray regime. As here, this is synchrotron self-Compton. This is external Compton components here. Most likely it's actually radiation from the broadline region and the dusty torus that serves as seeds for making the gamma rays in the Compton.
Then how do you compare this peak of synchrotron photons peak and also high energy peak? What are the basic difference in the conditions or parameters in the system? Dominating high energy peak dominating synchrotron peak or otherwise? what are the difference in system parameters of the system generating that kind of emission?
Now the difference, it's the difference between high synchrotron peak BLR objects and the low synchrotron peak blazars. So one is simply the presence of the external radiation fields. So in HBLs, most likely we have clean environments that we simply don't have external radiation fields. But also the LSP blazars tend to be more highly magnetized, which increases synchrotron over SSC, so kind of suppresses SSC a little bit. And in those cases, you have the stronger Compton cooling from the external radiation fields. That gives you typically lower energy electrons. So the difference is that in low synchrotron peak blazars, typically you have lower average electron energies in the chromium frame than in HSPs, which is the reason why you have in HSPs the synchrotron peak at much higher frequencies, because the electrons tend to have much higher energies there. So there's a couple of differences.
Hello. Very nice talk. So I have a novice question. Like you said, this beam is coming and then it's creating a knot, right? So this knot properties would be depends on the galaxy property or like the host black hole properties. So, and do we see multiple of these knots or single knots? And if we measure the distance from the main body to the knots, so does it tell anything about the host galaxy, means host black hole or the galaxy property?
Well, the galaxy properties are probably not so relevant, even though we seem to see most of these blazar type sources in elliptical galaxies, but that's probably more a consequence of the merger history, that they have a lot of gas in their centers just because they probably went through recent mergers, and that essentially destroys any spiral structures. But so in blazars, we do occasionally see in the radio images multiple blobs. In particular, in radio galaxies, we actually see several blobs along the radio jets that we can resolve. So we know there's not just one.
Yeah.
For the blazar models, one often assumes that there is one dominant emission model, but even that is most likely not the true answer. We have several cases where there's clear evidence of at least two emission zones playing a role in the broadband emission. And so we know that there are multiple zones.
So does it tell anything about the host black hole? Because galaxy property, you said it's not that correlated, but does it tell anything about the host black hole?
Probably not so much about the black hole itself, more about the regularity of the accretion flow, I would say.
Oh, okay.
And also it's most likely interactions of material within the jet after it has been ejected. So it's probably not telling you much really about the black holes.
Thank you.
Sachi.
Can you make a statement that if the high energy peak dominates the synchrotron peak, then hardening model can explain the CD?
I can't say that. No.
Okay, so we have one question from YouTube. I will just read it out. So can polarization measurement constrain the strength and orientation of magnetic field, its alignment and spin with the jet properties and origin of such a strong magnetic field? So can polarization measurements give light on any of this?
Polarization does generally not really depend on the strength of the magnetic field. It depends on the order and the structure of the magnetic field. So it tells you about the degree of ordering of the magnetic field. You have rotations like that. That probably tells you something about probably some helical field structures. But that's about as much as one can.
Not on the strength or the origin of the magnetic field.
Sorry?
Not on the strength or the origin of the magnetic field.
Right. Orientation, of course, the polarization direction will be perpendicular to the dominant magnetic field orientation. So it tells you something about the orientation of the magnetic field, but not really about the strength.
No, so the question was about origin. I mean, from what is the origin of this magnetic field? So that we will not get too much information based on polarization measurement.
Right. Yeah. Polarization measurements won't
Yes.
answer that.
And the other part is there a role of any other subatomic particles?
Oh, sorry?
Subatomic particles. Other subatomic particles, do they play any role in generation of this high energy radiation?
In hadronic model, they can,
Yes.
right? In hadronic model, we are producing pions, both charged pions and charged muons can also produce synchrotron radiation. If you have sufficiently high magnetic fields, then you can actually have synchrotron signatures from the pions and muons before they decay. But of course, we know they decay on microsecond timescales, so it has to be strong magnetic fields for them to be able to radiate before they decay.
Yeah. So I think if there are no more questions, let's thanks Professor Boucher again. And I will request Professor Pallamaraju, Dean PRL, to give a small moment to Professor Boucher. Yeah. So for online audience, we will sign off now. Thank you very much for your participation.